the two examples we're going to work with are the null space and the column space. And so these are examples of subspaces tied to linear transformations. And so we're going to talk about them a little bit in the linear transformation world. I'll try to make connections in these to the old world that you know from pre-calculus. Mostly it's just new vocabulary to do familiar things, and it's pretty cool, kind of fun. So we'll probably mostly talk today about the null space, maybe a little bit of the column space. On Tuesday, when we pick it up, we'll finish this stuff off. So let's start kind of at the beginning. So remember the homogeneous equation. So remember, it's the homogeneous equation if you have this equals 0 on the other side. And so this can be written in the form, matrix form, AX equals 0. And in this case, our A matrix is the 5, 21, 19, 13, 23, 2, 8, 14, and 1. And so the solution set is the set of all vectors X that satisfy the matrix equation. And so we're going to name this set of solutions the null space. Okay. Maybe you're like, what did we just do? What we said is that the set of non-trivial solutions to the homogeneous equation is the null space of A. Phrased another way, writing set of non-trivial solutions of the homogeneous equation is a lot of words. Null space of A is a lot more concise, kind of saying the exact same thing. So the null space of an M by N matrix A, which is written as Nul A, is the set of all solutions of the homogeneous equation AX equals 0. In set notation, the null space of A is the set of all X's such that X is in Rn and AX equals 0. You've probably seen things like this before, where you had, remember you had things like f of x equals 0. That might be a little bit more familiar from the old dark world. And if you ever see an equation that says f of x equals 0, what are you looking for? Like back in pre-calculus, what is it that you were looking for? So I'm hoping what you can see already is that we've solved the homogeneous equation for non-trivial solutions. We've done this in the past. We've also found x-intercepts in the past. So I'm hoping what you're seeing right away is that this is a new way of doing something that you've done in the past. It's just a new vocabulary for something that's actually familiar. So in example 1, so let's let A be the matrix that's above 5, 21, 19, 13, 23, 2, 8, 14, 1. And I want to determine whether the vector u equal to 5, negative 3, 2 belongs to the null space. And so if I want to determine whether u is in the null space, I'm going to check by finding A times u. It'll equal one of two things. What are the two things that AU could be equal to? Okay, and if it's equal to 0, that tells you, that u is in the null space. Or it could be equal to not 0, in which case that would tell you that u is not in the null space. So we're going to do some complicated math here and multiply. 5 to 1, 15. And I could multiply by 5, negative 3, and 2. And when I multiply, what am I going to get out? A whole bunch of big numbers. Are they all 0? 0 for the first entry. Okay. From Felix, 0 is that for the second entry? and from twee that they're all 0. Sweet. So we got 0 out the other end right here. So that tells us that U is in the null space. Yeah, thank you, Megumi. Thank you, Kevin. So in the picture, you could think about it as saying that we have our U vector here, and our U vector that's in the null space is being mapped to 0 in the image. So the image of U is 0. Okay. Now that's a little bit different than asking ourselves what is the null space. So if we wanted to find the whole null space, so let's maybe extend the question a little bit. So if I want to find the null space of A, and sometimes I'll use parentheses like it's a function. Sometimes we will just write it without parentheses. So if I want to do that, what I need to do is I need to solve AX equals 0. Okay. Which I'm tracking right. Copy. Boom. Hey, what do you know about that? It worked. So this would be like saying you take that matrix A, we can now augment with 0 and row reduce. And when you row reduce, you're going to get out 1, 0, negative 2.5, 0, 0, 1, 1.5, and 0. I'm hoping that folks are seeing what's going on. This is actually an augmented matrix, so we do have a free variable, x3. And so this is telling us that our solutions are x equal to x3 times 2.5, negative 1.5, and 1. Remember, you have the 1 here because x3 is the free variable. Okay, so we're not going to write our null space this way. We're going to conclude from this that we would write that the null space of A is equal to the span of this vector. Or if you wanted to multiply by 2 so you didn't have any decimals, that would work as well. What I want to point out is that most of this should be familiar. Like, we did something old. We haven't done anything new here, but the only parts of this that are new are one, the vocab of null space, okay, and 2, the idea of writing the null space as a span, writing a subspace. So the notation where you'd write the null, like how do you actually write the answer? So this span here would be equivalent in the picture. That would be like the whole line. So we're spanning a line, so that's going to give us a line. And the U that we found earlier was just 1 point on the line. Got a question from Gerald. So if we have only the trivial solution is 0 the only vector in our null space? Yes. Yeah, and special things happen when the only thing in your null space is 0. Like good things happen. But at the moment, we just have not good things. The null space of an M by N matrix A is a subspace of Rn. Equivalently, the set of all solutions to a system AX equals 0 of M homogeneous linear equations in N unknowns is a subspace of Rn. So here we see that word subspace showing up again. In order to be a subspace, what 3 conditions must be satisfied? It must include the 0 vector. It must be closed under addition. It must be closed under scalar multiplication. The fact that I've already said this like 5 times today is probably a hint that it's important, right? Like these conditions, they're not hard, but they come up over and over again. So I'm trying to help drive them in. So let's look at the 3 conditions. So first of all, we could talk about whether the 0 vector is there. So is the 0 vector an element of the null space of A? Yes. And how do I know that? I know that because A times 0 equals what? Equals 0. Now it's a little bit tempting to see these 2 zeros as the same. What dimension is the orange 0 living in? From Ryan, it's in Rn. And what dimension is the green 0 living in? It's living in Rm. So this one is in the domain, whereas the other one is in the image or the range or codomain. Okay. So we have 0. Yay for 0. Okay, so secondly, we want to show that it's closed under addition. So we will let U and V be in the null space of A. What do we need to show? So if U and V are in the null space of A, what does it mean? What do we need to show? From Andrew, that's exactly right. We need to show that U plus V is in the null space of A. Thank you, Alex, for the same thing. And I think Ben, and for Gerald, it's not so much that U plus V equals 0, it's that A times, we got to look at A times U plus V. Okay, so A times U plus V, we could do some complicated math. This would be the same thing as AU plus AV, which would be the same thing as 0 plus 0. Why is it 0 plus 0? Why do I know that these things are 0? I know that AU equals 0, and the reason I know AU equals 0 is because I know that U is in the null space of A. That's what it means to be in the null space. So we've got, notice what we just showed. We just showed that AU plus A times U plus V is equal to 0. What does that tell me? So we've got the A times U plus V equals 0. That tells me that it's closed over, we'd say under addition, not over addition, but, or you can add. We get that U plus V is in the null space. We can do the same thing for scalar multiplication. So we can let U in the null space of A and C, it's a scalar, in R be given. So then we would look at A times CU, which would be CAU, C times 0, or just 0, which in turn tells you that CU is in the null space. So it's closed under, the purple says it's closed under addition, the black says it's closed under scalar multiplication. We're here on example 2. And just kind of continuing to plug away, again, looking for examples of subspaces. We're going to let H be the set of vectors in R3 whose coordinates A, B, and C satisfy these 2 equations. 2A plus 3B equals 5C, and 6A minus 5C equals 2B. And we want to show that H is a subspace of R3, and thankfully, we're given a little bit of a hint. So let's follow the hint. Let's create these two dependence relations. And so what I'm going to do to start with is I'm going to take these two statements and I'm going to write them in a more standard form. So I could have 2a plus 3b minus 5c equals 0, and also 6a minus 2b minus 5c equals 0. And this should think of a homogeneous system of homogeneous equations. And so we could write this in matrix form as 2, 6, 3, -2, -5, -5. This would be our matrix A. And then we're going to multiply by A, B, C. And this should be equal to 0, 0. Here's our... So you have your AX equals 0. And so the question basically amounts to finding all the x's that make this true. So the set of all x's such that AX equals 0. But this is the same as saying that H is equal to the null space of matrix A. And we know the question is asking us to show that H is a subspace. One way to show that something is a subspace is to show that zeros in the set, show that the set is closed under addition, and so that the set is closed under scalar multiplication. Another way to show that it's a subspace is simply to say that it is something that we already recognize as a subspace. So in this case, you can see that H is equal to the null space, and we've already showed that the null space is a subspace. So therefore, H is a subspace. Yeah, back. Questions? All right. So in example 3, we're asked to find a spanning set for the null space of matrix A. So a spanning set for the null space of matrix A. And so I'm not sure if you remember what a spanning set is. So a spanning set is a set of vectors where we can really span them and get the whole space. And so in order to do this, we need to solve AX equals 0. And the reason we're solving AX equals 0 is because we care about the null space. So since we care about the null space, we'll solve AX equals 0. I'm going to erase this stuff above because I think it's distracting. Okay. So solve AX equals 0. And so This means we're going to end up having this matrix. Okay. And so we can dump this thing into our Texan friend, row reduce. And you notice, you might see right here that it's already in echelon form. So the actual row reduction here is pretty straightforward. You'll end up with 1, 0, -7, 6, 0, 0, 1, 4, -2, 0. So let's think about what this is telling you. This is telling us that x1 is equal to, looks like 7x3 minus 6x4. x2 is equal to -4x3 plus 2x4. And then what does it tell us about x3 and x4? Yeah. From Ben, Megumi, Abed, Gerling, Gerald, Evan, Kevin, Tweet. It's free. Happy free variables. Okay, so this takes us to this place where we're saying that x is equal to x3 times, looks like we've got 7, 4, oops, that's a -4, 1, 0, plus x4 times -6, 2, 0, 1. And again, that one is showing up here in this one, and this one is showing up here in that one. Okay. So what this tells us, the actual question said find a spanning set for the null space. And so what we're saying is that our spanning set is these two vectors. Is this spanning set unique? Are there other spanning sets? So,
since we have a free variable, I don't think it's unique.
Yeah, but that's right. So it's not unique. Think about it. You could add a multiple of one of these and it would still span, like Evan said, any linear combination of them would work. So you could add more vectors and get the same thing, or you could replace these vectors. Like I could replace the second vector with 2 times it. So instead of having -6, 2, 0, 1, I could have -12, 4, 0, and 2. And that would also be a spanning set. So what's important here is that that we will never have a linearly independent spanning set that has less than two vectors for this particular space. Any questions about this example? All right. So a couple of properties of null spaces that contain non-zero vectors that we can see from the last example. The spanning set generated using the method we just used is automatically linearly independent. Just to be clear, I'm not saying that all spanning sets are linearly independent. I'm just saying that the ones you find using the method we just did, that those ones are linearly independent, assuming they're more than just zero. So the number of two, the number, there's an of isn't missing, isn't there? The number of linearly independent vectors in the spanning set of null A equals the number of free variables. In the equation AX equals 0. So we ended up with one vector for each free variable. And you'll see that happen over and over again. Questions? So up to this point, we've been talking about what space? What have we been talking about so far? So thank you. So we've been talking about the null space. Okay. Thank you to Ryan, Felix, Sammy, and Croy. So now we're gonna switch gears and we're gonna start talking about the column space. So the column space of an M by N matrix A, written as Col A, or you could also, sometimes we'll write like Col A like that, is the set of all linear combinations of the columns of A. And so you can think about this as if A has columns A1 to AN. So here, in this case, these A's are representing columns. If you have those A's representing columns, then the column of A is just the span of all of those columns. And so theorem 3 says that the column space of an M by N matrix A is a subspace of Rm. We could prove it, but if you think about it, the column space is just the span of a whole bunch of vectors. And so what happens when you span things? You make linear combinations. So that's how you take care of addition and scalar multiplication. And then 0 has to also be in the space. Well, 0 times even one of the vectors gets you that 0 is in the column space. So it's a pretty straightforward thing to show that it is a subspace. So in example 4, I want to find a matrix A such that W is equal to the column space of A. So let's see how this plays out. So we can go from this this set of all vectors of the form B minus C in the first component, 2B plus C plus D in the second component, 5C minus 4D in the third component, and D in the fourth component, where B, C, and D are real numbers. We can think about this as being some AX where you have 1, -1, and 0. Oh my gosh. The dentist is calling me to reschedule. What can I say? 1 minus 1, 0, 2, 1, 1, 0, 5, negative 4, 0, 0, 1 times B, C, D. Okay. Just making sure you're seeing what's going on. Here's maybe here's the 5 and the 4, 5 and the minus 4 that are matching with the C and the D. Okay. So we just wrote W like W is the set of all things in this form here. And so if we want a matrix A such that W equals the column space of A, boom, we've got our A. So here's the A. I don't know if I like orange. That's kind of painful. Sorry about that. And then we want to talk about the column space of A. So the column space of A would be the span of the span of those 3 columns. You'll notice that we're going to separate out, if we're talking about span, since you have span here, we're going to have commas in between the vectors, and you could use either curly parentheses or normal parentheses. I'll tend to use the curly braces there for span because it sort of denotes a list. So the question asked us to find the A. We found the A, and we wrote out what that column space is. Questions about this? All right. So this next example that we're going to look at is, I'll say, kind of a big deal. Did I skip over something? Sorry, I skipped over one line. So the column space of an M by N matrix A is all of Rm if and only if the equation AX equals B has a solution for each B in Rm. That is, so the column space fills out the space if and only if you can get everywhere in the range, if it's onto, if you will. So let's look at this example 5. And I tend to like this question, or versions of this question, because it asks you to do kind of to look at multiple spaces in the same question. So given the matrix A as follows: 1, 1, 3, 1, 2, 1, 5, 4, 1, 2, 4, negative 1, answer the following. So first of all, I want to find the space such that the null space is a subspace of it. So let's start by thinking about dimensions. So I've got A as a 3 by 4 matrix. So if I multiply by an X, what are the dimensions of that X? Yeah, from Evan and from Gerline and from Gerald and Richard, we've got 4 by 1, right? Because those inside dimensions have to match. And so we're going to get B's out the other end. And what are the dimensions of the B's? So the B's are going to be 3 by 1. Good. Okay. So when we're talking about the null space here, we're talking about x's. And so the null space is a subspace of R4. Okay. The little symbol there is a subset symbol. That's not a subspace symbol. I'm just saying in this case that the null space is a subset of R4. Okay. And then the column space, these would be linear combinations of the columns, is coming from the B's, which are in 3 dimensions. So the column space of A is a subset or subspace of R3. Okay. So in this next part C, we want to find a non-zero vector in the null space of A. Remember, 0 is always in every subspace. So just saying find a vector is kind of boring. You just say the 0 vector. So we don't want to do that. Come on. Come on. Come on. Okay. So we're going to try to solve AX equals 0. So if we're dealing with the null space, then you can always think about this as needing an AX equals 0. And then we can row reduce. Y3, I got a question from Gerald. Remember, the column space is linear combinations of the columns. And so think about each of those columns has just 3 components in it. So if you add up, if you took 1 of the first column and 0 of the other ones, you'd end up with a 1, 2, 1, which is just a 3-dimensional vector. Okay. So we can row reduce text and style. And when we row reduce text and style, we end up with 1, 0, 2, 3, 0, 1, 1, negative 2, 0, 0, 0, 0, 0, 0. So how many free variables are there? So 2 free variables. And so we're going to end up with our null space being described by having 2 vectors in its, at least 2 vectors in its spanning set. So we get that x1 equals negative 2x3 minus 3x4, x2 negative x3 plus 2x4, x3 is x3, x4 is x4, where you get x equals x3 times negative 2, negative 1, 1, 0. Something like that. Come on. Sorry, my tablet's not Assuming the way I expect it to. So the question asked us to find an example of a non-zero vector null in the null space as well as the null space. So if I wanted to find one vector, what do I need to do to find one vector? What do I need to do here? From Gerline, that's exactly right. I need to pick a value for x3 and x4. It doesn't really matter what values we pick. We're not going to pick 0 and 0 because that would be cheating because they told us we needed a non-zero one. But we could do the next best thing. We could choose like, I don't know, how about like 1 and 1 just for the sake of having something to do. So if we pick 1 and 1, what's the vector that's going to be in our null space? -5, 1, 1, 1. Come on. Something like that. If you'd chosen a different x3 and x4, you would have gotten a different vector. But this is a vectors in our null space. This isn't all of the null space. Question also asks us right here, says find the null space of A. And so if we want to actually find the null space, we're going to take advantage of these vectors here and say that the null space of A is equal to, can I just list off the two vectors? Is that right? Is this my null space? Yeah, from Andrew. What I need is I need the span of the vectors. Okay, something like that. It's a pretty sketchy curly brace there. All right, questions so far? All right, so in D, we're asked to find a non-zero vector in the column space. Finding a non-zero vector in the column space is hecka easy. So here, what you could do is you could simply grab one of these columns. So like 1, 2, 1 would be an example of a vector in the column space, or 1, 1, 4. Or maybe I could take both of these columns and I could add them together. And if I added those two vectors together, 1 plus 3 is 4, 3 plus 5 is 9, 4 plus -1 is 3. These would be a couple of different examples of non-zero vectors that are in my column space. Okay. So this one was A1. This one was A3 plus A4, where the A's are the columns of matrix A. Okay. So in part E, we're asked whether a specific vector is in the null space. So if I want to know if a vector is in the null space, is that an A in the second column? I think it's a 9. So if I want to know if a vector 1, 4, -2, 1 is in the null space, I could mess around with row reduction and seeing whether it's in the span and all that kind of garbage. But another way of doing it is I could just multiply it by A and see what happens. So if I've got this A that I want to test out, I could say this vector that I want to test out, I could say A times 1, 4, -2, 1. And if it's in the null space, what should I get out? From Gerald and Alex and others, I should get out 0. And so I'm basically testing, is this true or not? And you can go through and you can multiply. And in this case, it ends up being true. So the vector, and I'm not multiplying it out, but you can multiply it. So the vector is in the null space. Okay. How about, why don't you pick a vector? Just you pick a non-zero vector. Give me 4 smallish numbers that are easy to work with. I got a 3, 2, 2, 4. Oh, I got a 3, 5, 4, 3. How about that? 3, 5, 4, 3. That was coming from Gerline and Ben and Juan and others. So if we want to test that vector, we would take our A. So our A matrix is a given. That's the 1, 1, 3, 1, 2, 1, 5, 4, 1, 2, 4, -1. And we're going to multiply it by this thing that you gave me, 3, 5, 4, 3. And we're going to ask, is it 0 or not? So I think I got 3 plus 5 is 8, plus 12 is 20, plus 3, I got 23. So what can you already conclude? Yeah, you got stuff here, blah, 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 blah. But you can already conclude that this is not equal to 0. So that would tell us this vector right here is not, do the element sign with a slash through it, is not in the null space. And thank you to Ryan, Felix, Juan, Tui, Megumi, Abed, and Alex for that. So that's how you'd figure out if a vector was in the null space. If you want to know if a vector is in the column space, you're kind of stuck with row reducing. So here, if you want to know if it's in the column space, then you've got to solve AX equals this 1 minus 1, 4. So this would be like taking your vector 1, 1, 3, 1, 2, 1, 5, 4, 1, 2, 4, -1, and augmenting with 1, minus 1, 4. And what are we looking for? What's our question asking? we want to know if it's in the column space. How will I know if it's in the column space? Yeah, the question is it consistent? And so we row reduce here, and what matters is that you end up with it's consistent. So I'm not going to put the, I guess I could write it down. Doesn't really matter. Well, yeah, it ends up being consistent. Like that's what matters. And so since it's consistent, therefore the vector is in the column space. Okay. Questions? All right, so I'd like to go through the this long list on the next page, and I'd love to get some readers again. I felt like that was good. So if you would like to read, if you could raise your hand and I'll call on you. And what I'd like you to do in this case is when you're reading is to read both parts, the two ones. And so, for example, if I was reading the headers, I would say, I'm trying to contrast between the null space of A and the column space of A for an m by n matrix A. And so the null space of A refers to AX equals 0. The column space of A refers to AX equals B. So is there someone want to raise their hand to read off the two ones? To unmute and read it off. Elijah, you want to read that off? So you're unmuted. Cool. Sammy, go for it on number 1.
So I read like the null A column and then the column A column.
Yep. Yeah, you'll read this stuff right here.
Yeah. All right. So number 1, null A is a subspace of Rn. And then number 1, column A is a subspace of Rm.
Cool. Somebody else want to take, Seche, you want to take 2?
I'll take it.
Okay, go for it, Kyle.
All right, so for number 2, null A is implicitly defined. That is, you are given only a condition, AX equals 0, that vector in null A must satisfy. 2, column A is explicitly defined. That is, you are told how to build vectors in col A.
Cool. Thank you, Kyle. Seche, yeah, for the third one?
It takes time to find vectors in null A. Row operations on matrix A0 are required. And it is easy to find vectors in column A. The columns of A are displaced as are formed from them.
Yeah, exactly. Thank you. Abed, you want to take 4?
There is no obvious relation between null A and the entries in A. For on column A there is an obvious relation between column A and the entries in A, since each column of A is in column of A.
Let me let me just pause there for a second. So when we say null A, this is the null space. Come on. Null space of A. And when we say column A or col A, what we're saying, it's not the columns of A, this is the column space of A. So just trying to help you on the folks on the vocab. So somebody want to take number 5? Alex?
A typical vector in V, or a typical vector V in the null space of A has the property A times V equals 0. A typical vector V in the column space of A has the property that the equation AX equals V is consistent.
Oh, thank you. Someone got 6 on the home stretch. Evan, number 6.
Given a specific vector V, it is easy to tell if V is in null A. Just compute A times V.
Mm-hmm.
Given a specific vector V, it may take time to tell if V is in column A. Row operations on the augmented matrix are required.
Yep, that's what we just did. Good call. So the null space of A equals 0 if and only if the equation AX equals 0 has only the trivial solution. And in 7, the column space of A is all of Rm if and only if the equation AX equals B has a solution for every B in Rm. And 8, the null space of A is 0 if and only if the linear transformation X to AX is 1-to-1. And the column space of A is Rm if and only if the linear transformation X to AX maps Rn onto Rm. So in that last one, you have 1-to-1 on the null space side, and you have onto on the column space side.